The very, like, one of the first days that it was not working.
Hello, dear friends. Let's discuss paper, lightweight message tracing for debugging wireless sensor networks. So this is the overview of my presentation today. First, we'll start with some introduction, background. Probably not many of you heard about what wireless sensor networks are, so I will give you some information on that. Then I will spend the bulk of my presentation on the cadet system. How do you cadet system description? One thing I haven't found in the paper is what stands behind cadet. Cadet. So there is no, it's not abbreviation or anything. I guess just the name of the system. Anyway, then we'll spend a couple moments on the fault case studies and empirical evaluation. But if any discussion points would arise, I'm willing to spend additional some time to discuss them further. All right, let's start. First of all, what is the wireless sensor network? I guess it's important background that everyone should know. First of all, it's a network of specially distributed autonomous sensors that are capable of monitoring some environment conditions. People say you can use them to monitor radiation, breach conditions, and many other things. First of all, right, maybe some of hardware guys would be interested in knowing how do they look like. Well, I did some Google search and this is what I found. So a company called Libelium makes and sells these sensors. So as you can see, they are not extremely capable. Well, they're not much more capable than your TI graphing calculator. Well, think about 40 megahertz, very small amounts of flash and RAM. Though currently they start supporting even SD cards. In SD cards you can put up to 2 gigabytes. So this is year 2015. The authors work on the sensors that I will show on the following slide. And this sensor, one of them they mentioned in the paper, it's Talos B, was made by Crossbow Technology. And it was about year 2005, I believe. So as you can see, it's has lower frequency and maybe not as capable.
Also in a more reasonable price range.
Yeah. So the thing is, right? This sensor, it costs $100. Could be cost $100, and in order to properly observe some system, you need probably, well, in the paper they mentioned 100 nodes or modes they call it otherwise. So yeah, it's in chip, and funny thing, they're capable of running their own operating system, which is called TinyOS. So imagine, right? It has less memory than your flash drive, right? And it's capable of running operating system.
So that operating system is just a bunch of small code.
Yeah, of course, it's a small operating system, and this is usually modes or nodes that are expandable with sensors. So, for example, Libelium node is capable of checking radiation using Geiger tube, and is capable of connectivity via GPRS, which is your cellular network, or Zigbee radio, and GPS to get its position. And it's all very low power. They claim that theoretically from this battery, the node could run for 1 year. Well, impressive. And the typical deployment of such nodes would be as follows. This is GPRS model. So you have a cellular tower, whole bunch of sensors that are measuring radioactivity, and they translate the data towards the cellular tower, and you can get the data. Now, so with VSN or wireless sensor networks have a whole bunch of problems that you probably won't expect on the regular server system or regular distributed systems. Well, in addition to very common node and link failures, you have issues like problems with the software, infrastructure issues. For example, you put a node in some remote location where you don't have radio propagation, good radio propagation. Apparently, you have data races. You can have such issues as because you have fairly small amount of memory on board, you can happen that you will overwrite previously recorded data points and so on and so forth. Unexpected environmental factors. Since you usually deploy them in the wild, well, who knows, maybe squirrel or crow will like your mode or node and will damage it. So a whole bunch of issues arise. And then when
So
you...
which one of those are they taking into account?
So regarding...
Bonus ones.
So, the point is as follows. This is the set of issues that might arise. And now, how would you detect on, like, you think there are potential issues. Now you want to detect where the issues arise. Are it on the sender side, like a tiny node is misbehaving, or it's on the receiving side, or there is a link failure. So it's kind of the system that they propose. They're saying that we can more reliably to tell where the issue is.
So one way of looking at this as well is that these are nodes that might even create a self-organizing network where there wasn't one before, and they have to deal with lots of complex protocols, and maybe there's even a bug in the protocol. So they just have a low-level system that could feed information into figuring out what any error might have been in theory.
By the way, one of the test cases that they observed is an issue in the protocol where you get unexpected message, and they were able to figure out where was this unexpected message. Anyway, so
on the,
and now,
so the environmental factor.
so the thing is,
Actually, that's not environment.
well, in their evaluation and their testing for the case studies, they haven't actually deployed this system in a while. They used simulations to check for the fault case studies, and then to measure energy, they use just a couple nodes.
So you can ask yourself, what is the impact of an environmental factor? And it might be something like an unreliable connection, right? And so that's the kind of thing you can simulate well. What would happen? Would the protocol still work or not if there's an unreliable connection? You should have a protocol, or you should have some system that works whether or not there's an unreliable connection. Having an unreliable connection is actually okay. Your protocol or whatever you're using should be able to withstand that. So an environmental failure that leads to a software failure is a bug. An environmental failure that is tolerated is okay.
And I might raise this following point, then since the nodes are not as powerful, there is simplification on the protocol side. So maybe, it's not your typical TCP connection with multiple checksums or something. It could be very simplified to transfer as few bytes as possible, because apparently transmission of the data is one of the most expensive operations that these sensors might perform. Right, and now, okay, imagine you have this sensor network and you want to debug for issues. Well, you have a whole bunch of issues that arise from the low-powered nature of such devices. If you try to do runtime debugging, obviously you will have high runtime overhead. So it's almost impossible for real-life deployment to do so, because your node will run out of battery and cease to function. So you don't want to constantly do debugging and constantly replace the batteries. Heisenbugs. I like this word, Heisenbug. So apparently it's like a Heisenberg effect. It has no relation to the, what is it? Huh?
Uncertainty principle.
No,
No
there's no relation
relation to
to the
Breaking
famous TV
Yeah,
series.
Breaking Bad.
Yeah.
That's
No
what-
relation to Breaking Bad whatsoever. No. Yes. Yeah. Then, if you do offline debugging, then you have. Well, I don't exactly understood it. They claim you have large amount of memory to deal with this.
The difference here is that online debugging would be like connecting GDB to a remotely running process and interacting with it.
Yes.
Offline debugging would be collecting data and analyzing it post hoc. So you've got to record that information, ship it off somewhere, and then look at that data after the fact. Right?
Yes. So I would, I guess if you have 100 nodes, even 100 tiny nodes will produce lots of data.
They will, and you have to worry about even just the data on a single node or a
Mhm.
single node because you got just so little space.
Okay. Yeah. And then
So wasn't the issue was that they were not able to debug the problems which were occurring because of out of order messages and stuff like that. And that was the problem with the offline.
That's
With the postmortem approach, there, if you try to like analyze the traces, it was not.
that's a problem with existing approaches,
Yeah.
not a problem with that just underlies the approach in general. So this is fundamental. That is a constraint, and existing approaches also have those issues, which we'll get to.
right. Then they mention a couple specific issues, but let's go over it. Right, and then they highlight 4 particular wireless sensor network constraints. So first of all, right, you have resource constraint shown on the hardware, message losses, we discussed already, unreliable connection, out of order reception, that's an interesting one, right? So your node is sending messages, 1, 2, 3. Well, they can arrive in a different order, right? You send him 1, 2, 3, you get 3, 2, 1, or
Can you-
3, 1, 2.
Can you instead explain local purging?
Yes, and purging. What is the purging? Well, so how it works? Node collects some data, and then it's periodically wake up its radio to do radio transmission. Now, local purging is when your local trace storage become full, and what you do, you overwrite it. So, yep, it will be as follows. I can illustrate. Let's say you have a ring buffer on the thing, right? So you have 1, 2, 3, 4. Now you have this much memory, and now you want to put 5, 6, right? So what you get? You start overwriting 5, 6, and then you have a transmission. And what you're sending? Well, you can send something like 3, 4, 5, 6, or you can send 5, 6, 3, 4, something like this. Get the whole buffer and send it as it is. Okay? So that's a purging, where the node locally start deleting the data. Apparently, very common for such small nodes. Yeah. Yeah, it's done in order to save energy, right? You don't want to keep your link up.
And what was the issue with local purging? The point?
We will have illustration later on.
It actually relates to issues that you saw in Project 2 a little bit, oddly enough. Not exactly the same, but there's a similar concept to it.
Okay, that's a good observation that you will think about later. Right. So now, what the authors propose, in short, they claim novel message tracing scheme. They decided to use per channel sequence numbers, which is a different from Lamport clocks that I will discuss later. They introduce address aliasing, very clever technique in my opinion. So essentially, address aliasing means follows. Node will talk to several neighbors of it. I guess we can illustrate it very nicely. Let's say we have a node with some scheme. This node will talk to its neighbors. It won't talk to all of the nodes in the network. Therefore, we can, for this particular node, we can create aliases instead of using full, I don't know, let's say address, IP address, right? IP address will be 128.0.0.7, let's say, right? Some IP address for this node. And therefore, in order to send a message for him, it should put this into trace. Like I send a message to the node with this IP. No, instead this particular node will have 1, 2, 3 aliases. And then we'll have special table that will say, well, you know what, it was 128.0.0.7, something like that. Or it's opposite. Therefore, in a trace, and a trace is just like a text file or something, it will, instead of I send a message to this address, it will say, I send to the S1, send to 1. So it's 2 characters only, less space, save lots of time, money. Now, right, so that's address aliasing, and then this claim that...
Just a second.
Sure.
Let's say we have to keep that table.
We have to keep this table, and they do keep it.
Yeah, the 1 to 100 and some. The mapping from the ID, the alias address to the actual IP address. But let's say if we have many neighbors, so in total we have 1,000 nodes. And
It's not the common case.
So that's the kind of thing that would be protocol and moat use dependent. Usually what's going to happen is that you'll spread your moats out across a wide area because you don't need to get a whole bunch of dense information about one location because they've got sensors, right? So they're probably gathering some physical information. So you can have them spread far apart and you might have 4 or 5 that are close to each other.
But still, you need to maintain that table. Like you need an extra thinking about maintenance of that
And they
table.
do that. And they do that. And apparently, even though you maintain this extra information on the node by using less space, you can save lots of.
On which node? Do they keep it on every node? In the cluster?
Yes. It's local information. So
It's local.
So if one node goes down and then comes back, how would it get the information again?
So if one particular moat goes down, then you will have essentially lost whatever trace information is on that moat. And you'd have to perform some sort of reconstruction process, which is a more complex scenario than they discuss. Can you do things like trace reconstruction from a set of partial trace information from different modes? That's an interesting problem. That's an interesting thing in the context of reliability and distributed systems. But that's something that's tough even with fully powered devices that have storage.
The reasoning for doing alias, address aliasing, is it just to save the few bytes of not having to record multi-IP address or whatever the larger physical address?
Yes, one of them. You save few bytes. Apparently, byte by byte, you get huge savings.
So suppose you have 10 messages from your neighbors, right? If you have the large address stored once, and you use the short address 10 times, already you've got savings. You probably had more than 10 messages.
Yeah. Yeah, you're saving a few bytes per message.
Yep, that's it.
Yeah. And then another thing inside, they say, okay, well, in normal wireless sensor networks, most of the messages still appear on time, get delivered and get sent on time. So there is no out of order delivery, most of them in order. So we can use this to get some additional savings. Yeah. Okay. Now, paper contribution. Well, pretty much we discuss contribution, what they done. Yeah, a novel tracing technique just discussed. Then they show effectiveness of their technique using tiny tracer simulations, and then using actual nodes, they show that they have trace size reduction and energy savings.
So when you say tracing technique, what are they tracing in particular in this paper?
In this paper, sends and receives.
Right. So there are different things you could trace. And they mentioned that there's other work that traces control flow. And in this one, what they're tracing is message flow.
So this node send some message to that node, that node receive or not receive the message.
Yeah, I didn't understand something. I didn't understand was tracing control flow. What is
That's project 3.
that? Oh, like path?
Yep.
Oh.
Control flow would be a subset of message flow, right?
Not necessarily, no. No. There's a relationship between them potentially, right? But recognizing that you've received a message, a particular message from one peer,
Mhm.
and that you've sent a message to a different peer is different than recognizing the path that led from one of these events to the other. One of these is recognizing the flow between units, and one of them is recognizing the flow intra-unit.
Okay. Oh, I see. Okay. All right.
Okay, so now next thing probably we discussed, right? So existing approaches, they think that we have lots of energy, we have lots of storage, we have good and reliable network bandwidth, and so on so far. Not happening with nodes, sorry. Now, so the trace-based debugging of distributed systems, this is also what you've been asking for, what they're trying to do. Well, the idea is that we want to preserve causal ordering of messages. Causal is a nice word in the sense it's like which message happened after another. We want to know, not exact time, but just like general ordering of sorts.
And you can think of this as being potential influence. Which messages have the potential to influence a later message? If one node receives one message before another, that's an indication the first could have influenced the second.
Yeah. So traditionally they use Lamport or vector clocks. Well, Lamport clocks apparently very popular among wireless sensor networks, and
But the
use these.
influence doesn't matter here. The influence of the messages.
The influence of messages does matter here. They want a very tight association. We'll see, right?
They just tell. Why do they? Okay, let's see.
I mean, the influence would be as follows, right? Some sensors checking for some information, movement, and there are.
Oh, the concurrency, for example.
It's not exactly concurrency; it's that they.
Concurrent messages.
So there is a whole bunch of nodes, and they want to elect the leader of the nodes that will talk to the server later on. So they need to somehow vote who is the leader. So
there is a notion of synchronization, which I think is maybe what you're getting at, your confusion there. But I think you can continue, and we'll highlight these
Yeah.
issues.
Probably not many of you heard about Lamport clocks before. So I took a pen and I found what Lamport clocks are from Wikipedia. Thanks, Wikipedia. So the idea is that we have, it's just as it says, right? We have a process, it increments a counter before each event, and then once there is a send or receive send event, we are sending this counter value with the message, And then on receiving side, we will increase the counter accordingly.
Have we seen this before?
Left the clocks.
The large blocks, which we saw in the last.
Okay, this is exactly what the last paper used. Not even vector clocks. This is what the last paper used. This was their fence mechanism. Right?
The shared count.
Yeah.
So apparently now you know how you had to write the critique for the previous paper, knowing that the Lambert clocks have many issues, right? So there is.
The last paper actually took advantage of these issues. But continue.
But theoretically you can argue that it's solved, not it. Still, issues was not solved. And so anyway, right? So there is a clock value now depends on multiple nodes, and since the nodes are unreliable, so there you have it. You depend on someone and it fails, and you with nothing. Now we have less opportunities for compression. Apparently, since you need to send this information, and the way you have to keep since the Lamport clocks are global, you need to keep the address of some sort from where it came from.
You need to. You don't actually need that. You just the nice thing about Lamport clocks, and this is Lamport just recently won the Turing Award in part for this and his other work in distributed systems.
2003.
More recent. I think. It's just a local counter. That's it. That's all it is. But there are a few issues here. One is that the value changes with every event. So there's no repetition, which is what compression takes advantage of. There's no repetition.
Concurrency then.
And the other issue is this first thing, you depend on multiple nodes. So we're taking a notion of partial dependencies. Say, I depend on the third event from node A, and we'll speed up, don't worry, and the second event from node B. And that will increase my count to a given scalar value. Some other node might depend on node C, and a message from node C and a message from node D, and that will increase its count to 2. We'll have the same count at 2 different nodes, but representing a count influenced by different messages. And so if these 2 nodes interact, they'll say, oh, we're both at count 2, good enough. They don't recognize that they got to count 2 because of different messages in the back of the system. But those causal messages have orderings that were at, say, 0 and 1. And so there's a total ordering imposed on the partial order. But it throws away the information of what led to the total ordering. So that projection of the partial order onto the total order is this loss of information with multiple dependencies.
Which is both its attribute and its.
That's what makes it more efficient, and that's what throws information away that they want.
Yeah. So it's benefit and its drawback.
Yes, exactly.
And is that because per event we implement the counter per event? Is that why the concurrency, so we cannot capture concurrent events?
It does capture concurrent events. It doesn't capture precise causality amongst concurrent events. Right? I can't distinguish, if one guy's got a count of 2, another guy's got a count of 2. All we know is that if there was some common causal relationship, then it would be accounted for, but there may not be any causal relationship, and we can't tell exactly what these relationships were. We have a common notion of progress, and that's it. Okay.
So, yeah, with sensor networks, you don't have any assumption. Let's get into this Lamport clock issues that we just discussed. So nothing, we cannot detect the order properly, since this is out of order message arrival, right? We have, we know, yeah, all we get in this diagram is that we receive something from thread 1, node 1, and we also get a tree, right?
Yeah, yeah.
So, and from this, essentially, it's hard to understand.
All it's doing is maintaining a notion of local progress, right? So you get a new message, you increment your count because you progressed. You don't know how this relates to the other events. Yeah.
So, this is another thing. By just looking at the trace, you cannot, with a good
Whether one
confidence,
was-
tell whether message 1 was lost or whether message 2 was lost. Yeah, by really replaying this trace, no way you would be able to know. And this is your favorite purging, right? Black thing means you purged everything that you knew before. So that's why if you look and
So
see,
you purge everything means you rewrote everything?
well, in this case, yeah, so as you can see, P0, right, P0, we have this black square, which means in our trace we left only with messages 2 and 3. You have no idea that you ever sent message 1. And yet, for the P1, you get purging at a different stage, and therefore you cannot, with a good confidence, replay afterwards
Yeah.
how exactly the messages were sent and received.
There's no notion of a consistent cut at which things were purged, which is actually the notion of a consistent cut in a distributed systems, in distributed systems, is its own difficult topic.
Yeah. So if you have time afterwards, look over these diagrams. Home. And the main question that the authors ask is how they can enhance control flow traces so they can help with better diagnostics of the faults. And this is the rationals between the system that they devised, CADIT.
Compression-aware distributed tracing.
Version of the distributed tracing. So this is what it means.
Anyway, continue.
Where did you find it? Compression hour distributed?
I figured it out.
Oh.
Wow, this is a major insight of the paper.
Continue.
Right, so idea, right? Nodes talk only few neighbors. We can use trace to infer the contents of the message. And in the common case, messages aren't lost or arrive out of order. Normal case, everything goes as fine. So this idea, optimize for the common case, which is prevalent, and then be capable of handle out of order or other issues. So and then by optimizing, make sure it's compressible. So this is the idea. Design advantages. Now, two key techniques that the author used in their system is address aliasing, just discussed before, have some table, use the shorter names, and then you have a sequence number. Yeah, so we keep last sequence number sent and last sequence number received on with a particular partner. Partner is a node with whom we talk. Right, and this is the algorithm. So, do we want to go over algorithm? Yes?
No, if you explain it was exactly like, it was more like a pseudocode.
Yeah,
It
so
is a pseudocode.
this is pseudocode. The idea is essentially you look always for alias information, and then look using this alias information. You look for sent and received sequence numbers, and if you, in case of sending, you always increase 1, and you keep it locally on a node. So you don't try to send it with a message to the alias. And then upon receive, no, actually you do send with a message, but on the receiving side you do some fancy defense.
You send what with the message?
Hmm?
You send what with the
Sequence
message?
number and the address.
We message sequence number.
Right, right.
Yes. So you do send it, but then on the receiving side you have some ideas how to handle them.
So
No.
you just check for the out of order or missing messages.
Yeah. And now, if you look on the traces, we would be able to, with high reliability, understand what happened during the analysis. So in case this is what happened, but this is what we get. So now we can get, okay, P1, it sent, first it sent to P0 message with number 1, and P0 and sent to again to P0 message with number 2. Now P0, what we get here? Well, we got message from P2, doesn't care about it, but now we get out of order. So we understood, okay, we get first message number 2 from P1, and then we get message number 1 from P1. Okay, so we got out of order.
Yeah.
And
And
we
you can recognize it.
able to recognize it exactly. Now, with to understand whether we received message or not, and which message we haven't received exactly, we get it. P1 send message 1 and 2. On P0, what we get? We received only message 1 from P1. We never received message P2. So, this is an issue. We now know that the last message that was sent by P1 was never ever received. And we know that maybe if it will continue, we know that there is some issues with the list. Or if it just one happened, well, environmental issue and so. And now purging, by the way, was a typo.
So I was thinking about this. I think there may be some other issues related to this. They may have had the right thing down there and the wrong thing in the diagram.
In the diagram.
Yeah. So,
Right.
so
Should I modify the slide and?
no. I mean, the slide is fine. We can talk through this. Because there isn't a whole lot left. I think just the empirical evaluation is after this, right?
Couple case studies and empirical
Okay,
evaluation, we
okay.
can glance over it. We
yeah.
want or not.
And then you mentioned speeding through the case studies. We can do that. So if you look at the ordering 1, 2 in P2, this kind of reflects a notion of logical clock, right? And increasing the ordering based on logical clock. But that might not be consistent with this notion of maintaining the per neighbor information, right? Because we've never sent a message to P1 before. So I think maybe that first message to P1 should be sending 1 back to P1. And that's inconsistent with the logical clock notion, but consistent with the neighbor-based
This
notion.
one?
Maybe.
No, we got purging. We forget that we ever sent it.
Yeah, the one back down. So there's an inconsistency here. I agree. Now we'd be throwing information away then. We'd be throwing away the dependence information between 1 and 2, but maybe we could reconstruct that from the trace of P2.
Disagree. Because, right, P2 will send us it will be S, P1, 2, something like this.
Well, the issue is that if we have this per neighbor counter, right, then the first message we send to P1 should be 1. Yeah,
Okay.
because we're no longer using logical clocks, right?
Yeah.
Now we're using these per neighbor counters where we have this pair of,
Oh, yeah, right.
what's the count of the last thing I received from this neighbor? What's the count of the last thing I sent?
Yes.
Yeah, it's
Yes, yes.
sequence
Yeah.
number.
Probably they wanted to save time and we used the scheme from the Lamport clocks.
I think there are a few issues here. Actually, I think this paper was written much longer originally, and they trimmed a lot out.
Wow, it was much longer. Good. Yeah, a lot.
And they trimmed a lot out, and as a result of that, they had to change their diagrams, and they removed their discussion of the diagrams. At least that's, I noticed there was virtually zero discussion of what these diagrams meant, which is a bit of a problem. I think the issue here is that they're still using the Lamport clock notion up above, and they should have updated that. So I think the tracing plot was right, the diagram's wrong.
Oh, okay. Yeah, so there is issue.
Yeah.
We're gonna send a message to the authors if you ever saw this video. Okay, so now case studies. Just real glance over it. First of all, they analyzed Leech is a TDMA-based clustering protocol. So now they found out, it's all simulations by the way. They found out, right, if we increase number of nodes to 100, we observe data drop, and in a later case, throughput drop. So they think, okay, why? And using Lamport clocks, Lamport clock-based traces, no way they would be able to understand why. But using caded trace analysis, they were able to understand that there is a issue with failed link between cluster node and cluster head. And the failure was due to join is one of the messages of this TDMA protocol. Join message collided, and hence the issue was. Now, fix previous bug, found other issue. Now, again, increase number of nodes, fix previous issue, throughput drop. Why? And the issue was because the debug message interfered with TDMA send sequence and led to them to discover an implementation fault. So essentially, what I understood is that there was some message sent, and they expect and receive, and then out of nowhere, there is another message being sent, and it was breaking everything.
So what happened was they had a buffer, a send buffer, and they would store the first message in this buffer, and then they overwrite essentially part of it with the second message.
So this was their bug.
No. This is a bug in protocol, in an implementation of the protocol. Okay.
Of Leech protocol. Right. Then was another case studies with some perimeter checking, but I think this one is more interesting. Is that we have a directed diffusion. It's where you can request where the sync node can request some information from other nodes. Do you have something? Leave it to me. And now they said that some node B start observing longer message rate from node A, and they wanted to find out that where the issue was happening on some node B or node A, whether node A is not sending or whether node B is not receiving. And so they took the traces from two nodes, and they were able to compare them as on the diagrams before and find the issue where it happens. So using Lamport clocks based traces, it was, they won't be able to do so. Now to evaluation, real quick. First of all, they compare to liblock traces. They made several assumptions as described here. Now, they made these assumptions in order to bring liblock closer to how cadet operates. So it's all described here. Now, I will skip over all this notation and the formulas. All you need to know that if you put actual values instead of this Greek and Latin letters, actual numbers for how often do you send messages, how big are the messages, what are your losses. You would be able to calculate gamma n, which is the amount of trace generated by a single node using cadet. And then similar thing you do, and you get amount of traces.
I had a question.
Yeah.
How do they get the probability for messages coming into that particular node or messages being received? Is it empirical?
That's the kind of thing that would be determined by the underlying protocols in the problem domain. You would configure that. Like in the real world, you would actually essentially configure those parameters for how you want the network to behave.
And they just want to, afterwards, they want to understand, okay, how small are logs, traces generated by cadet when compared to liblog traces? Like, are they significantly smaller? Well, turns out they are. Turns out they are. This diagram, all you need to understand is that this relation that I put before, which is gamma n versus beta n, it's in a range of 15 to 45%, which means this one, just small fraction, even with of what liblog generates. So we have significant reduction in the trace size in terms of number of bytes. And
are you talking about the justification? Like, so is it because the clock basically increments the counter per event and per node? So if there are so many nodes, then
one is that you have the issue of these nodes having large IDs, and those get stored in the trace. And the other is the compressibility because there's no repetition inside the existing log stuff.
If they talk about the repetition, then
They didn't really discuss too much about the actual notion of compressibility. I don't have a concrete guarantee that what I'm saying is the exact reason, but it's the only reason that seems to make sense.
And then just for this graph, PL is the probability of a message to get lost during transmission. So as you can see, they vary from just a few percent to up to 90%. So it's like only 90% of messages lost. Significant amount. Yes.
I think this
Okay,
is
what is
like
9.9?
0.9 is so we have probability of message loss, and this one is the per out of R, how many messages arrive out of order, I believe.
Okay.
Yeah.
probability of
Yeah, what is
PL is a probability, so
Because Mr. Arrives in here. So this is.
I'll never.
So
Yeah,
0.9,
Never
0.5 is how many messages arrive out of order. They arrived eventually. And then PL is how many messages are being lost.
So I thought that the y-axis is pi, that is the probability that the messages arrive in order, and x-axis is PL.
No. Y-axis is this relation. It's 100%.
Why would it show two probabilities?
Right. And at the end, so you get on the different benchmarks, we can find out that we have energy overhead on the lead block and small energy overheads using cadet with all the benefits that ensure. Yeah, obviously benefits are different for different benchmarks. And then, but what do you pay for energy savings?
Yeah.
Well, you pay with a little bit more of memory usage. So just so you know,
Sure.
data memory is a memory where you put your variables, and program memory where the application is being stored.
I'm actually really surprised that they have compressed program memory. That makes no sense to me. I think they should have explained that.
Okay. You chop it out or something. Anyway, so this is the.
So by data memory, they mean the AA map and E map stuff?
Trace.
And also the trace?
All data. Okay. So
What is
the
data
compressed actually takes up more. That's what I would expect in the program memory, because the extra instructions for doing compression should take up more space. I can't explain why for two of the benchmarks, compressed takes up less space in the program memory.
So I didn't. What I didn't like about these plots is that where they start their scale, right?
Yeah.
100.3.
Well, I would still expect that even with a baseline of uncompressed, you have to add instructions to compress.
Mm.
So the relative things, I think, the right column should always be more than the left column there. For when using compression data memory, it makes sense that you should use less space if you're compressing the traces. That makes sense.
Yeah, so the data memory includes all the mapping as well
Yeah.
as the message
Yep.
traces?
Yep.
Both.
Or it should, yeah. That's the underlying model. So the executable data and the data you can write are two completely different partitions of memory.
So if you're compressing something, so you had a network address. Okay, there are only three neighbors. There are three network addresses.
Yep.
Now, if you add that network address across all the addresses, and if you compress it, it's still repetitive.
Is it still what?
It's still repeating, right? So if the network address is say some 128 something, and if that was repeated 10 times, if
Okay.
you do a compression, ultimately it will be stored as one. So
So the issue is the entire aggregated information. That's not the only thing they've got, right? There's more information than just that inside
right.
data line.
So the other part. So basically, what I thought what they are getting the benefit of the trace compression is because of the Lamport clocks which they modified, and not exactly because of this. Because if this is repeated 10 times, and if you do a compression, ultimately it will be stored only once.
Because Lamport clocks.
Lamport clocks is
and-
where they are getting the actual benefit from.
Part of it, yeah.
Because they explained that.
Yeah.
So initial clock is 1,
So-
and then the differences, they are just storing the differences.
One and
So
one.
since most of them are sequential,
You still have these temporary windows though, where you still have to worry about these underlying IDs to some degree.
But they explained that in the paper. They
So-
mentioned that because Lambert clock, if it is only one,
So we want to take this offline so we can at least let
Okay,
you go
Yeah.
to
So
the
conclusions: efficient, consistent, resource constraint aware, and then helps to facilitate diagnosis of faults.
Okay. Yeah, thanks.
so basically the